This is the second talk that I give after COVID, like in person. And the first talk I gave maybe a month ago, when I wanted to erase something, I was pressing the button because I'm used to teach online with the iPad. And that's how you erase. And I look really silly trying to erase. At least this time I'm not doing it. Happy? Also, I teach many courses about machine learning and those kind of things. And I'm used to ask people many times if they're following me. So I'm not so used to be right now with professional mathematicians. So I'm sorry if I ask if you have questions many times, but that's my job to ask if people have questions. Okay, so I will, as I said, I will talk about column functions. And as I said, this is related to the existence of geometric quotients, the existence inside some category of equivalence relations and the existence of treating in from a geometric point of view equivalence relations, right? So let me give you an example. If you think about an algebraic space, like this very classical notion of algebraic space like Artin, right? So you have an italic equivalence relation, and then your quotient scheme or a variety with respect to this equivalence relation. It turns out that even when the equivalence relation is étal, you might not be living in the category of algebraic varieties or in the category of algebraic schemes or whatever, right? But still you could define a function that has all the categorical, axiomatical properties that one would expect from so-called geometrical objects, right? It turns out that this same thing happens to some theories inside O-Minimality. It happens with the definable sets inside O-Minimality structure, right? I mean, it's not necessarily that you will use the language of categorical algebraic geometry, but the properties, like the geometric properties that you get from this quotient, are as good as the geometric properties that one would expect from a function, right? I mean, I'm not saying that quotients are algebraic space. I'm not saying that quotients are algebraic stacks or something like this. It's just that instead of using functors to do geometry, we're using these first order formulas, and still some of the things you would expect they're smooth. Okay, so this is the idea behind the column functions, and I was so I will go a bit faster, and I just want to point a quote by Grothendieck in the paper of time topology, which he calls the okay, so he calls he writes this the concept de choix anodin, which I'm not sure what's the best way to translate it, but he's talking about some obvious choice that you need when you quotient or when you considering equivalence relations. So this is one of the things that he wants his same topology to satisfy, right? So I invite you to read exactly what he means. This is just one paragraph where he mentions, but I mean those scaling functions and in general the elimination of imaginaries that I will talk about is what I am pointing out as one of the tame properties he would expect from a theory, from a topology or topology like. Okay. To the best of my knowledge, I don't know if people have made a precise statement from the. I mean, if there is a precise statement saying O-Minimality satisfies exactly what Grothendieck meant in his paper, and there is something with respect to his stratifications or this Devisage-like theory, but there is nothing about this, and I think it's very interesting because we model theorists or logicians think about those scaling functions as something crucial for any theory to be important. Okay. So here is the definition of a scaling function. So structure as scaling function if for any formula, and I'm thinking about this formula right now as a formula without any more parameters. So this is like formula, but I mean, you could also have parameters. Let's think of this case first. So let's suppose that I have n+1 variables in this formula. Okay. I think I already wrote. So it has if for any function for any formula here there is some other formula that I will call phi tilde, and this formula is a function. I mean, this is the formula that defines the graph of function, but I will just write this is a function from Mn into M. Okay, that satisfies the following property such that the following formula is true. So whenever I have x1 is xn, so I am voiding. I was going to first, but whenever I have not using this x0, there exists, if there exists an x0 which satisfies the whole formula, I mean the initial one, and if this set is not empty, then I can witness this existence only using this last n parameters or n variables, meaning x1, xn, x1, xn. This formula holds, right? Okay. So I have n+1 variables here, meaning I have a set which is definable in n+1 Cartesian product. And what I'm saying is that if the first coordinate, I mean the projection, is non-empty, right? If this happens, then the whole formula, I mean the whole to witness the
like an implicit function.
It's like an implicit function, right? Yeah.
Like they're solving for the other variable.
Exactly.
Locally.
Yeah, exactly. It's like this étale behavior, right? Okay. well, I mean, this seems to be a strong statement, right? But it turns out that any O-minimal theory extending semi-algebraic sets satisfy this assumption. And the proof, I mean, it's something that an undergrad who knows model theory could finish it quite quickly. It's almost immediate. I mean, you need to use of course the seventh axiom. But I mean, if you state it like this, as Ernesto mentioned, it looks like an implicit function theorem. But also, I mean, whenever a theory has scaling functions, I can do quotients, as I said. So assume S is some definable set inside here, and assume that E it's an equivalence relation living here. Okay, then whenever you have scaling functions, you could also find a definable formula which goes so a definable function, sorry, which goes from M to N, so here, right, into maybe another set that maybe another Cartesian product. I might not have control over this this M, right? It could be larger, it could be smaller. There is nothing that I will do. There is no restriction. This function is definable, right? And this formula, it's this function witness the equivalence relation, right? Meaning that whenever I have X E related with Y, then it's because this formula knows it, right? Okay, so the key statement is that this function should be defined. Okay, so let me say it again. If I have the scaling functions, then for any definable set and for any equivalence relation, I can find a definable witness of the equivalence relation.
It's like there is some fundamental variations.
Yeah. It's like right? Yeah, so there is a choice. Actually, those scaling functions are called definable choice. Yeah.
So the projection is the quotient.
Huh?
So the projection.
And so, yeah. Oh, of course, because the image of a definable function is a definable set, right? I mean, you just need to say there exists. Why such? Okay. And in this result where they prove this Hodge-like statement, they use this result to prove that the ring spaces that they are working with have geometric quotients. And geometric quotients, well, I mean, maybe I don't know right now the precise definition, but it's essentially this, right? Morally. Yeah, it's an infinite. Thank you. I mean, not all theories have. I mean, even not all O-minimal theories have this property. This property, you will find it as elimination of imaginary. Right? I think it's a very good name because those equivalence classes are imaginary, right? So they are not elements in our universe. They live in an imaginary universe. But if I can witness, I can point them using a definable function, then I can eliminate imaginary.
But then when there are no of these imaginary elements, should we understand this as these are the real quantities I need to work and I can no longer simplify the model?
I mean, you could always enlarge your structures, your theory with imaginaries. I mean, this is a classical construction in model theory. I mean, whenever you have a structure, you enlarge it with something called MEQ, right? So there you, by force, you have imaginaries. Of course, there you could prove you have imaginaries. I mean, it's closed because here in this larger, you could have new imaginaries, but I mean, the construction is intelligent and you eliminate imaginaries here. But theories that have elimination of imaginaries here are very are tame, right? So this work by Ruszewski regarding, and not the one with Kashan, but the one about Berkovich spaces, they strongly use that they in their theory you don't have elimination of imaginaries in the classical algebraic closed valued fields, but they give a precise definition of what the imaginaries are, and this is why you can rebuild all this Berkovich theory.
So how do you use Coulomb function?
It's not immediate because I stated this for X here. I mean, just for one variable, but yeah, I mean, essentially that's how you prove.
When having this phi is the same as
This is a sequence. This is a sequence of that. It's not immediate, but yeah.
not
No. In general, it's not true.
how would we like how could we define like a computable manner of verifying the existence of the exponent function? And doesn't this would rely more or less like first order logic somehow?
Well, it's as complicated as elimination of quantifiers. It's a dog proof.
These like
I mean, not case by case, but by understanding. For example, for algebraically closed fields, it's Gaussian elimination, right? I mean, it's a weak version of the Grassmannian.
but doesn't this sound like we have to be able to see the whole thing in order to begin the procedure?
Yes.
Because if so, then the vision itself will be the procedure.
Well, it's because in model theory, whenever you start building some tame first order logic to a structure, this is how you normally start. So you start asking, can I eliminate quantifiers? Maybe I can't eliminate quantifiers. Then in which language can I eliminate quantifiers? So which quantifiers do I need for I mean, you need to understand definable sets that are using quantifiers, and it's the same here, right? You need to understand which imaginaries you need to add in order to minimize that. That's how people normally proceed with this, right? So for example, there is a model theory for automorphisms, right? So you add the graph of an automorphism of the field, and then, well, it turns out there is no quantifier elimination in that case, but you need to understand which are the quantifiers that you need, and that's what. So this is the hard part of model theory, right? I think that, like, seeing this from the perspective of a arithmetician or a geometer, I mean, you have this, right? And that's pretty much how this this Hodge application started, like using all this machinery to prove that certain arithmetic sets are definable. These period maps are definable. Maybe you can't show they're definable using a first order formula, but you could do some tricks to make it definable. I mean, maybe it's not obvious that you want niche quantifiers, but if you have this result, then you know there might be a complicated, not computable formula that that is not using quantifiers, and then you win. Okay. So I have how much time? It's still 5. Still 4.
Yeah, it's a 4.
I don't know if there is any question about it.
So, which structure can have
So R and X has this property.
other
Not all O-minimals, but all O-minimals extending this have. So for example, R and that is R X. Therefore, you eliminate imagine. Okay. So this is like saying that I mean, in fact, in the complex algebraic case, you could define, for example, Moishes space, right? They are definable. Those algebraic spaces are definable over those fields. So you could think as anything that it's étal close to algebraic geometry, it's interpretable, meaning it's an imaginary. More complicated quotients is a bit difficult, right? Like stacks, there is no model theory for these more complicated quotients. Well, I mean, I'm not saying that it's not true. I'm just saying that no one has proved that part. So
But anyway, you end up with a set.
right, yeah, that's the problem.
You know, and stuff you would like to remember the automorphism, for example, the form.
Yeah, but I mean, in this, if the equivalence relation or the group action is definable, then I mean it's the same thing with algebraic spaces, right? So the quotient as a set is nothing, but the quotient with the sheaf it's something. So I mean the quotient, the set together with the equivalence relation, you recover the isomorphism class. So what I'm saying is that for the case of the stacks, there is no O-minimal result.
So then all moisture space can find
Yeah. I mean, there should be some restriction, but okay. Good. Okay. Then I said I will talk about the cell decomposition here. And this is something brave to say, but I know this is not entirely true, but no, it's not true. But I mean, it's on this spirit of stratification that Grothendieck asked in his article. No, so there are some results, some, I mean, close to the research. Maybe the closest to this is by him. There is also an O-minimal stratification. So the strongest O-minimal stratification was shown by him. And they were following stratifications like from top. Okay. I mean, but just to make it, just to say it again, I'm not saying there is this term for O-minimal, whatever, because I mean, it should be a quite general statement. There is no choice statement as Grothendieck asked, but there are some traces of his ideas in this O-minimal, which are actually here, right? And this cell decomposition is an actual here. So I will give an inductive definition of cells first, and then I will state the theorem of cell decomposition, and this theorem is used to define a notion of dimension. So, which are the cells inside the line, model theoretic line? First are open sets and open intervals, and just one. Those will be my cells here. Okay. Then let's say we know which are cells, or the cells inside Fn-1. Okay. And we will define two kinds of cells in the nth partition product. So the first kind of cell is the closed cell, right? Which, as you could imagine, is just the graph of a continuous definable function over over n-1 cell, right? So let's say that S is a cell inside n-1, and F is important. This should be a continuous function, right? Not only definable. S is function and also definable function. Then the graph of this function, right again, but idea, then X being here, so this graph is a cell. Yep. It's good. And then you also want these open sets, right? In the previous case, second case, say that F1, both F1 and F2 are definable functions and continuous function over M, right? For M, yes. Sorry. Okay. Then the following set is also a cell. So all X, Y living here, and so this S is here. It's a cell n-1, So then this should be n minus 1 times m, such that for all those y, let's satisfy x1x, x2x, all those pairs xy, which are bounded by continuous functions, provided everything is definable and S is a cell. This is also a cell, right? So this is a cell with it's a non-closed cell, right? That one. Okay. Okay. So what does the cell decomposition theorem tells you? I mean, and just one comment, you could imagine what the cell decomposition tells you is that any set is a finite union of cells, right? But this is amazing because we only gave a restriction over the line, over M, right? And still we inherit all this tameness from Cartesian products, right? So this cell decomposition theorem tells you if I have S any I have set, then S is a finite union of cells, right? But you have like stronger version of this, that if you have any function, any definable function into M from any definable set right now, so I'm not even asking that this function is continuous, then you could restrict this function into the cell decomposition of this S, right? And also you could you could ask, I mean, also the restriction of these functions will be continuous, right? So maybe the cell decomposition that you get from this point won't give you continuous restricted functions, but this theorem is telling you that you could find it a continuous restriction of functions, which is quite, it's how do you call it? It's an absolute like conditional or something, right? F is a finite union of continuous functions between cells. Right.
It's like by a cell decomposition aspect that you prove something like that. You have a graph and you want to use this like 4 colors or 3 colors to make some property, and then is enough to verify to each finite part of it.
No. That is the compactness term. So the compactness term tells you that if you have a family of functions which is finitely satisfiable, then it's satisfiable in some larger model, right? So the result that you're saying is because of compactness theorem, but this is something purely geometrical, right?
There's no uniqueness here, though.
There is no uniqueness. Yeah.
So some cell decomposition is not continuous, but then if you refine it, you end up with.
Yeah.
But
You could
but
have
this is
more.
saying- This is saying nevertheless that all functions are
Piecewise.
or continuous functions.
Yes. Yeah. That's amazing, right?
That continuous functions are self-generated.
Yeah. And you could ask for more, right? So you could ask for tubular cell decompositions or even triangulation, triangulation or triangularization, no, triangulation, and it's okay. There are some cell decompositions even for tubular decompositions. Perhaps the best reference is Lloyd. I can pronounce it. I'm very sorry. I mean the second name. That's the best reference for those those more complicated cell decomposition theorems. It's from '96, I think, and it's deep. So his results are deep, and I've seen that many people from these modern applications of O-Minimality, they always quote his results, and I strongly recommend to read him. I think it's a very good reference. Okay. Well, something I didn't say is that we could, once we define what cell is, we could define what do we mean by the dimension of a set, right? So we could define the dimension of a definable set just as so if you have a cell of the second kind, then it means that the dimension grows, right? If you have a cell of the first kind, then it means that the dimension of the graph is the same, right? And then you could define just the dimension as the maximum of the dimensions from this finite union of cells. And everything works fine. It turns out this is a nice dimension. Right? So this is the kind of dimension we would like to work like a vector space like dimension. So all those fiber theorems work perfectly. They don't for continuous functions. They have wide properties even for differentiable functions, but the dimension is what we expect in the O-minimal case, right? And you even have some of those very nice results that people know for Zariski topology. So let's say you have a family of definable sets, right? So when I say a family of definable sets, you see what I mean, right? So what I'm saying is that there is a formula. So if this set lives here, then what I'm saying is that there is a definable set S living here, right? And then the fiber, so this is just the elements here, which satisfy the formula. So here you have x1, xn, and then you have beta 1, beta m, right? So if you fix the m betas, then you get a new definable set over inside mn. And then you could ask something about this function. So let's say you send beta into the dimension of S beta, right? So this from algebraic geometry, like algebraic geometry or algebraic closed fields, you know this is a constructible function, right? So this is one of those beautiful constructible theorems proved in Egea. Well, what do you expect about this function? First, this function is defined. What we want. Okay. And I mean, this function, I mean, we could be worried.
Automatically bounded.
Huh? automatically bound. Yeah. Sorry, I didn't say it properly. I will define it. Where? Right. Then. I'm gonna use the cell decomposition theorem to inductively define a dimension, right? So suppose you have S, any definable set here. Okay, so because cell decomposition theorem, then we know that this is a finite union of cells, right? So we could say that the dimension of S is equal to the maximum of the dimensions of S1 to Sn. Okay, so we still have a problem. We need to define it for cells, right? And any cell is either the dimension of this, it's equal to the dimension of the previous, because this is a cell, then you know there is a definable function from S tilde I into M, right? And then you will say that this is exactly the same dimension as this if Si is equal to the graph of this function. Okay, but the other case is that Si is not equal to the graph, but it's equal to a set like this, right? Those are the only possibilities for ourselves. And then
Dimension.
the dimension will be one more. Yeah.
In the description.
Yeah, and in this notation, yeah. Okay. Okay. Yeah. Good. Is there any other question about it? No. So about this one? Yeah. I mean, because it's a definable function, so I didn't say that, but all definable functions are piecewise increasing or decreasing or constant. So
But here it's a discrete value function.
yeah.
So
Oh yeah.
So it's not.
Yeah. Right.
Just discrete. Yeah, but no, not here.
And maybe you're asking what happens if something is infinitely definable, meaning that I need infinitely many formulas to point it. And in that case, well, I'm very optimistic about these things in O-Minimality, so I guess it could be true, but I don't know. So
I think what is true, but I don't, maybe you can tell it only, is that there is a stratification.
Yeah.
And then you have what you are in lower strata, but here there is no order. Yourself, so it could be various dimensions. And because you didn't order them, maybe you order them by dimension, then you can say, no, but of course, then it's increasing by definition.
Yeah.
I think it has to do with this. There is like something like that.
Um. Okay. Want to say something more about cell decomposition, but well, I mean, also this notion of dimension, it works well with what in algebraic geometry you call the local dimension, right? So if you say, for example, the dimension at one point is the dimension of the local ring, blah, blah, blah. So there is an idea, a very beautiful notion of local dimension in this sense, and which is compatible with the, I mean, in the field case, when you have the field structure, when you have the semi-algebraic sets, it's the germ of functions or definable functions. Okay. So I don't know if there is any other question. Yeah, the order. Decision. Okay. Oh yeah, this result is also good. Let's say we have some function, some definable function, and let's assume this set is open, right? Then for all d, for all natural numbers, I can find an open set here, open and for definable, such that the restriction of this function to this set is as differentiable as you want. So f restricted to this set is in CV. So I can shrink these open sets to make it as smooth as you want. In fact, there is a very nice seminar Bourbaki by Alex Wilkie, the one who showed that our exp is all minimal. And when he gave this seminar, it was still open if you could make it smooth, not just the differentiable, right? But later, perhaps at the beginning of the century, they found counterexamples, which are a bit pathological. But I mean, at least this, I'm sure it's true.
Probably,
Huh?
it's a quantifier that exists here or what?
Yeah, sorry. Yeah, as you see, we logicians, we don't use quantifiers. There is shrinkage. Yeah, and of course,
How
you want that the dimension of this is so you want this set to be large, right? You say you first there's a point where it's differential.
Okay, I still want this those code.
I don't have it, but I can send you the but I'm quite sure it's related to Pfaffian function. To those other O-Minimality structures. I know where it is, and I can send it.
Probably big, but this
Yeah, it's large inside you.
Of course, otherwise there would be.
Yeah, that's what I was saying. Okay. And something that it's beautiful, I think, from an algebraic geometry point of view. This is following the statement. I'd like to say that this is a tame result, right? This is a tame result. We have, I have three results, which I call them tame. Oh, yeah, the definability of the dimension. You agree with me? This is a tame result, and there is this other one, which I find it beautiful. So once again, let's assume we have a definable family here. Okay, definable family means that there is a definable set whose fibers are those subsets. So then there exists some natural number n such that, so this is a uniform for the family. So this is uniform set, a uniform natural number, such that as beta, those fibers are unions of connected components. It's quite clear that you could, I mean, from cell decomposition, there are definable sets. You could make, you could always find the connected components. But what is beautiful is that you have an absolute bound for those definable families, right? Which is one of those uniform results for authentic.
So this is just a number, one number.
One number, yeah.
To rule them all.
One number to rule them. Or
This
to
is
rule the fibers.
reasonable spec, of course.
Huh?
This is very reasonable. spec,
Yeah.
of course.
I mean, it's very reasonable, provided I convince you that O-Minimality is tame. But if you think about the definable sets in R and S, X, you have, in principle, you have quite wild
No.
definable sets, right? So
It's very surprising there.
yeah, exactly. And if this, even for semi-algebraic sets, is a bit obvious, right? But then for analytic sets, it's not. Depends on the family. Depends on the first order formula that defines this one. So as you notice, it looks like we are doing geometry as old geometries, right? Not this Grothendieck style thinking about geometric objects. This is a lot closer to Andre Weil's.
This is grown.
What I mean, his last
Early growth.
yeah, but early Grothendieck, this is not early Grothendieck. I mean, it looks very very weak, but I mean, all those applications that they found.
You mentioned this because of this quote about introducing numbers as coordinates is an act of violence. What does it do?
Okay, I have a few minutes left. Maybe I stop here.